So today we have one of our research grant recipients speaking on his research, which is in progress. The title is Post-Glacial Plant Succession in the Trinity Alps Wilderness. And Sebastian is a student at Cal Poly. And I think this is like research in progress, like he's not really done yet. But I think that'll probably be easier on us. And then maybe when he really gets done, we'll do something else. Well, maybe we'll go to Trinity Alps. That'd be a good, cool thing. So post-glacial plant succession in the Trinity Alps, and I'll let him sort of explain who he is. He's a member of our chapter, and he's had a helper. He'll be here too. Okay, so we change microphones now, and if anything doesn't work, just let me know, and then if it's okay to make me nervous, we just don't want to make you nervous.
Oh,
okay.
It's already gone out the window.
Oh,
we're good.
You want to see?
I think you should be good standing.
We can give you a second microphone if you don't want to trade it back and forth.
Oh, you have a second one? That might be amazing.
Yeah.
Versus an awkward
I don't
handoff.
know that it works, but
Oh, wow. Oh, you want
they'll tell us. They will.
You want the big one?
Okay.
Okay.
You just hold on to that one. Don't give it back to him, or it will cause problems.
Okay. Yeah, so as kindly introduced, Sebastian Evans. I'm a grad student at Cal Poly Humboldt, working on a sort of passion project about the post-glacial plant succession in the Trinity Alps wilderness. And I'll kind of give you a rundown and introduction so that you guys know who you're supporting as dues-paying members. I'm the recipient of the micro grant, or one of the recipients of the micro grants that you guys put out this last year. And it helped fund this research and kind of get it out of the door and get it up and going.
Hey, Sebastian, sorry to interrupt. Can you a little more direct yourself in front of the laptop so Zoom can see you?
Oh, hello.
Oh, that's better. Thank you so much.
Okay. All right.
So change this.
That's maybe I'll do that. Yeah. Can you still see me now?
Yes.
Okay, perfect. All right. Yeah, I'll just move it around as needed. Yeah, so I work under Dr. Rosemary Sheriff and Dr. Lucy Karoulis. Lucy's here. Thank you for being here. They're great advisors. They helped get this project off the ground and also hired me as a grad student. As was stated earlier, I work at Cal Poly Humboldt trying to get my master's with this project. Okay, there we go.
Shut off the lights. Yeah. People need to express their eyes.
Okay.
All right.
So just some acknowledgements to get out of the way with first. I'd like to acknowledge the people who have lived here, unceded, managing, and observing. It's no surprise to all of us here that there have been native peoples living in this area for a very long time, practicing wild management of our wild landscapes. And they've been here a lot longer than researchers, than people who are among us today, looking at and observing and collecting data on these plants. These include the Wiyot, the Hoopa, Karuk, Yurok, Talawa, Shasta, and other members. They've been here just so much longer than us, and we really owe it to them to pay them at least some acknowledgement of their actions before we got here and performed our data collection today. I'd also like to thank my advisor, Dr. Rosemary Sheriff and Dr. Lucy Karoulis. They were really instrumental in getting this project off the ground. They put up with a lot of really horrible renditions of thesis proposals and methods proposals, and worked with me really closely through the summer to try and get this project off the ground. And it really came down to the wire, and I can't thank them enough. And then I'd also like to thank the members of this chapter. This grant meant a lot to me. It allowed me to go out and collect this data. And I think it's really great of all of you guys to be providing funding and support for the new age of botanists and people that are coming up, studying in a place that we all can collectively say we care about a lot. So thank you all. I'd also like to thank two grad students and undergrads that have helped me a lot. In the top right is a very small person. That's a better image later on that's zoomed in. That's Courtney Copper. She's another grad student working in Lucy's lab who helped me out on this research trip. these are big mountains and very small people, so having the extra hands helped a lot. And then in the bottom right there is Forrest Horben, the gentleman standing to my left, your guys right. He was instrumental in helping me get all my gear up there, helping troubleshoot problems we were having. You can have the most dialed and buttoned up system for collecting data, and as soon as you get in the field, it seems to all go wrong. And so Forrest was my rock, definitely been influential, and also taught me how to be a better botanist in the same time. So who am I? At a young age, I was already introduced to the outdoors. I liked climbing rocks, as you can see here. I was really interested in natural ecosystems. My mom's a member of your guys' chapter here as well, and she brought me up in the world of botany. But on the flip side, I had a lot of interest in high places in Colorado, New Mexico, other alpine environments. I spent a ton of time recreating in these areas, and for a lot of my life, didn't really understand them wholeheartedly the way that a lot of you guys understand these plant communities that we have around us in these special places. As that kept going, I found myself following a very different career trajectory. I ended up working for the Forest Service for 4 years in New Mexico on a hotshot crew. And that was kind of an interesting little deviation from the academic trajectory I'd been on, seeing the firsthand effects of climate change, of mismanagement of public lands, and a lack of understanding of our plant ecosystems and how that could have these awe-inspiring and terrifying repercussions for people and communities and habitats as well. At the end of my first season on that hotshot crew was the first time I was introduced to the Klamath Mountains. This picture here is taken on the McFarland fire. It was a large fire that happened in 2021. It was the first time I really got to set foot into the Klamath Mountains, and doing so in a way that felt like I was benefiting public resources and kind of doing my part to protect landscapes felt great, but at the same time left a lot of questions I had unanswered. And that was kind of the reasoning as to how I found myself here at Cal Poly today. Pictured here is me, my dog, and Forrest working on the project I'm currently working on at Cal Poly, which is a vegetation mapping project. We get to go out and around all over the Klamath Mountain ecoregion, studying vegetation patterns, looking at communities, and trying to map and better understand just exactly what we have here in the first place, and how that might be used for management benefits in the future, and just understanding the broader ecology of the landscape. I work with some great students and members of CNPS doing this. This is Forrest and Copper at the foster cabin in the Swift Creek area of the Trinity Alps. We spend tons of time in the backcountry, bringing plant presses, staying in amazing places, and collecting data to bring back and share with the public, which is super important for us. That work mostly involves sitting next to a very heavy backpack, squinting agonizingly over perigynia and grass seeds, spending heaps of time in one place just trying to better understand our ecosystems. And a lot of the time we don't have the luxury of lab grade microscopes, then we have to deal with squinting instead. We get to see some amazing plants while we're out there. This is Helenium bigelovii, pictured with an amazing butterfly sitting on it. We're really lucky to do this kind of work, and it helps fuel our passion. It makes it a lot easier to go to work every day when you're going to see beautiful things. We also get to see some of the amazing landscapes we have here. Over here, we have the granite core of the Trinity Alps butted up against this metamorphic rock around it. So we're really in some amazing places. And we get to see some amazing specimens like this foxtail pine here, some of the biggest of the 5-needle pines that I've seen, just some amazing places that all inspired me to pursue this project of independent research. So with that being said, I'd like to turn it over to Forrest, who's going to introduce some kind of core principle things that you guys should understand to understand this project and what I'm kind of aiming to do.
So hi, everyone. My name's Forrest. I am by no means an expert on glaciers, but I will attempt to briefly define what a glacier is in the context of this project. And really what it is compacted snow that is formed permanent ice. There's several types of glaciers: continental glaciers, alpine glaciers, and oceanic glaciers. And in the study site, there used to be of the Salmon Glacier, Scar, it used to be one of the alpine glaciers. And these are large, compact ice forms that typically move very slowly over time downslope, and we see them forming beautiful geologic formations that we can see even long after the glaciers have since left and melted. They're highly variable in size and exist on all continents except Australia.
So this photo is a glacier in Iceland, which is very different than the glacier that we're studying here today. Much larger, but typified by these large crevasses. A lot of debris forms on them. They're pretty interesting places from the standpoint of a geologist.
And so ecological succession is also a foundational aspect of the research that Sebastian has been doing here. And just to define that real quick, it's something that we can see all around us happening all the time. And really, it's a series of progressive changes to ecosystems through the introduction of new species, either outcompeting species that are already there, or just adding to the species richness that is within the ecosystem. And we can see this can be defined in terms of statistically as either being a linear process or being much more of a random process that happens. And there's much debate over how exactly succession happens. And I think probably the answer is it depends, because there's so much diverse ecosystems out there. And there's two kind of basic types of succession that we see as primary succession and secondary succession. And on the glacier, what we're seeing is primary succession, which is actually quite rare in the grand scheme of things because it's only happening where you have a clean slate. So as the glacier has receded, we're seeing a completely blank landscape that is free of any lichens, bryophytes, any vascular plants. And so where secondary succession is something that we see commonly, where you have changes to ecosystems after disturbance.
Sweet. So the context for this study in terms of glaciation, the Trinity Alps are a landscape much altered by glacial ice. In 1960, this guy Sharp went up into the Trinities and he described multiple glacial landforms and sort of these hallmarks of evidence of historic glaciers in the landscape. This came in the form of cornice peaks, glacial lakes, and these large moraines, which are piles of debris left behind after the ice has gouged out a landscape. And this paper was kind of fundamental for a lot of the glacial research that's happened in the Trinity Alps since then. It described these massive areas that we frequently visit recreationally, Canyon Creek and Coffee Creek and so on and so forth, that were actually carved out not by rivers, but by glacial ice long term. This glaciation, you can chalk it up to being part of the Pleistocene, and that's a long way of saying it's part of the last big ice age that we had in the continental United States. So think of woolly mammoths and so on and so forth. After that, much more recently, we have this concept known as the Little Ice Age, or LIA, which caused glacial advance. So the glaciers have retreated since the Ice Age, and much more recently, around 1300, 1850, that kind of time frame, there's a period of global cooling. It's evidenced globally, but really in the Northern Hemisphere, and it's very well recorded in Europe, where there were significant crop failures, shorter growing seasons, and famines that were going on at the time for a period of about 500 years. Think of it as colder winters, more precipitation, more flooding, and all these impacts that affected crops in Europe. But in North America, we see this evidenced by this glacial advance. These glaciers are starting to regrow, or new glaciers are forming, and they're continuing those erosional processes. The ice is pushing down from mountaintops or growing further away from where it used to be. And again, in the United States, this is most clearly evidenced in several mountain ranges. It's evidenced in the Northern Rockies. It's evidenced in the Sierra Nevada. And Not a lot of people know this, but it's evidenced here in the Klamath, Mount Nika region. So in 1903, Hershey goes up and he is looking around at the geology of the landscape, and he notes that there are these three tiny glaciers. These three tiny glaciers, one of which was since kind of lost and hasn't been reassessed, but two of them were reassessed. And this is kind of the first literary inference we have of evidence for these glaciers existing in the Trinity Alps wilderness. In the 20th and 21st century, climate change trends lead to this glacial retreat. So these glaciers have grown during the Little Ice Age, and then as a result of climate change in the 20th and 21st centuries, they're retreating. And Justin Garwood published a paper in 2020 that elaborated on this and described this retreat, highlighting how climate change-driven effects due to a really rapid rate of retreat. So they weren't retreating at the same rate that they'd grown, they were retreating much faster as a result of higher summer temperatures, less winter precipitation, and I'm sure many of you guys can connect this to historic droughts that seem to have plagued California up until 2020. What this ultimately led to was the overall disappearance of the last two glaciers in the Trinity Alps, Grizzly Glacier being one of them, the larger of the two, and Salmon Glacier, the smaller of the two, retreating faster and disappearing earlier. So Grizzly Glacier disappeared in 2020, and Salmon Glacier disappeared in 2015. This glacier retreat is often cited as a bad thing, which it is, no doubt, a hallmark of climate change is glacier retreat. But in the same stroke, it exposed new alpine habitat that had been covered by ice, with the inability for it to support plant life year-round. And as this glacier is retreating, it's creating new substrate and new areas that are north-facing at high elevations, primed to provide habitat for alpine plant communities. This process that Forrest was describing, plant succession, it varies across a wide range of glacial sites. And no doubt succession has been studied in detail for a very long period of time. Even in light of glacier retreat, I think the oldest paper I could find was 1976, describing successional trajectories after glaciation, but it's variable. And what we're trying to kind of untangle here is how this succession is different in the Trinity Alps. One of the unique things about Northern California and the glaciers we had is that they were the lowest elevation glaciers outside of the Olympic Peninsula in Alaska in North America. So this is a really unique setting for a study like this to take place. And so here we have kind of the end result of what this after glaciation looks like. Here is Grizzly Lake, this amazing waterfall that spouts out of it at the top of this head wall. And up to the top left, you see this peak, that's Thompson Peak, rising just over 9,000 feet. And at some point in time, historically, that was covered in glacial ice. And as you can see now, it's really relegated to some of these late summer snowfields and presenting again this opportunity for plants to grow. So if we go through this historical context, we can see that as a result of really detailed study by Justin Garwood and some other researchers, there were these aerial photography, this aerial imagery that was obtained spanning from 1955 onwards through the 21st century. So we have 1955 on the far left and then two photos from 1972 on the right. They show that this glacier in actual fact was still in existence there. So I'm going to use my cursor and cheat a little, but there's glacial ice present here. So this is when the glacier is still kind of functioning as it was, but it's in its state of retreat. And using these images, this idea of a retreat sequence was able to be mapped out. And most recently, what that looks like is these recent kind of images right before the glaciers disappeared. Here you can see Salmon Glacier barely present at all, kind of relegated to this really shaded nook. And Grizzly Glacier is a little larger here, but still in a significant state of retreat. So the other thing we need to cover is the botanical context for the study, which Forrest will tackle.
So we wanted to look at the surrounding ecosystems that may be contributing species composition to the glacial scar. And so one of the primary habitats that we're seeing up in that subalpine zone is not a true alpine fell field, but a subalpine fell field. And this is rare within the Klamath Mountains ecoregion because it's not quite at the height where you get your true alpine, type of ecosystem where it's above the tree line. But in the context of this, there's the conditions that make it look like an alpine area where you have, you have low soil development and you have really high UV radiation with a short growing season and harsh conditions. And there's not a lot of invasive species, which was really amazing to work in an area where you don't have a lot of invasive species. It is definitely a gem. And then another ecosystem that we see a lot, on the highest ridges in the Trinity Alps and some other areas is the 5-needle pine forests. And these are a bit drier and really low cover of the 5-needle pines, as well as, you don't have a lot of shrub cover or herb cover. And this is a really rare tree. We see our foxtail pines and the western 5-needle pine. And both of those are really unique, and we wanted to see if we're seeing succession happen from either of these different habitats. And another one that is much more common, and many of us are probably familiar with, is the high elevation redford forests, and this includes the hemlocks as well, which, in congruence with the redford, really dominate the ecosystem a bit lower in elevation than what we're seeing at Salmon Glacier, but still it is part of the surrounding area of the study site.
So to get into what this might actually look like and give you guys some pretty flowers to look at, as opposed to just words and data. Up here in the top left, Campanula wilkinsiana. This is a rare plant, really, really rare. I've seen it one time up there, growing in and amongst the cracks around some of these perennial streams that flow within the glacial foreland. It's growing here right next to Ethereum disdentifolium, which is an alpine lady fern, another really beautiful alpine relic species. And then here, maybe a little more common, but equally as cool, Anemone drummondii, these famous Einstein heads of this fruiting body here. They look absolutely wild. And yes, they do feel as weird as they look. And then here down in the bottom middle is a really cool, rare huckleberry, the dwarf huckleberry bush, which if you guys know Dana York, Dana would say that just about anywhere else, unless he can put his eyes on it, it's probably not the rare one. But up here, growing in abundance, enough to where maybe you could or could not pick a berry or two to eat, there is this rare huckleberry bush growing really well and doing quite well around the area. And so we're trying to see here, paint a picture of what are the potential sources of these rare plant types and are they growing in this glacier? So that leads us into the questions that I really want to answer with this research. And again, I want to preface that this is not a finished product, and these are only trends that I can extrapolate from what I have so far. I have a lot more data collection and also a thesis to write at some point. But we wanted to know how plant communities change over time and how are they distributed. We really want to focus on the relationship between alpine specialist plants and generalist plants. So we're looking at, okay, are the Vaccinium scopariums, the rare huckleberries, are they growing there? Or are we looking at plants that we see all over the place? Is this an area that is harboring alpine endemics, or is it just a new spot for really competitive plants to grow? This has a lot of weight in terms of the conservation of alpine plant habitat, and really looking at whether or not the high country of the Trinity Alps is going to continue to perform as well as it is currently in harboring these alpine plants in newly exposed areas. The other question is, are there indications of competition increasing through time? An increase in competition can lead to certain plants being outcompeted. So say early on in the successional stages, this glacier is retreated, we do see some of these rare types of plants. Maybe they're there and that's great, but maybe over time they're being outcompeted by something else. And that's a notoriously difficult thing to tease out in terms of ecology. And so we set out to try and answer this question. This could result in the local loss of species, despite the biodiversity overall increasing. So you can feasibly imagine that, say there is one rare plant that colonizes quite early on, 3 more plants may grow in its place in a number of years. Overall, there are 3 species leading to a higher biodiversity, but we've lost that one hallmark plant, that one alpine endemic that we really care about that may not be found in many other places, given how rare this kind of community is to start with. And lastly, this is the question that I don't have the capacity to answer yet, but it's coming up in the next presentation, whenever that is. Is there potential for facilitative relationships to exist between non-vascular and vascular plants, and does that change through time? Mosses are oftentimes cited as one of the earliest pioneers in these alpine habitat areas. They can tolerate harsher site conditions than vascular plants often can. And so what we wanted to understand is whether there's a relationship spatially between these vascular plants and the mosses that are growing there. Are the mosses helping these plants get a foothold on this glacier? This relationship between these different plants and different clades and types of growth forms is often overlooked, but they play critical roles in ecosystem functionality. We've seen that in light of the understanding of how fungi interact with trees and how these networks are oftentimes much more complex than we originally thought. And this can help us in understanding the factors that lead to decline of these alpine plants. Say they require these interactions with mosses or lichens to live. If we see those interactions suffering over time, maybe that will give us some inference into why the decline of alpine plants is happening. So to answer these questions, we're going to go into our study area. Here we are, Arcata. We're all very familiar with the coast of Humboldt, but at least I was not as familiar until I visited the Klamath for the first time with this massive chain of mountains that lie just to the east of us, known as the Klamath Mountain ecoregion. I would personally argue that the crowning jewel of this is located here in the Trinity Alps. It's a giant granite core of mountains that were exposed, very similar to the Sierra Nevada, by a bunch of granite that was welling up under the surface and was subsequently eroded. These are the jagged peaks. These are the snow-strewn mountains. They're the places we all like to get our postcards of, and they're absolutely wonderful, and they're very remote and beautiful to study. So how we got there, we set out in August of this last year. This picture on the left is one of the first hurdles we had to tackle getting there. At this time of the year, there was a giant fire near Orleans, and it almost cut off our access to the study site. So pictured there is the backpack strapped to the back of Forrest's motorcycle and the plume of clouds coming out from that fire. So it seemed a little ironic that as a firefighter, I was going back to get back in the woods and a fire was stopping me, but that's all right. And then the other thing we liked to use was, and thanks to you guys, was this, which is a llama packing in a bunch of gear into the high country to get us back there with all of our survey equipment. This is Grizzly Meadows. And that's kind of just a short clip of what it took to get us back there and how beautiful it was. Llamas are amazing to work with, so thank you all very much for helping me get those. As we go, oh man, this is gonna be, okay, so yeah, the other thing I'd like to acknowledge in that is the people who helped me start to answer these questions and the people who helped to get me back there. Forrest Horrobin, who's been talking to you tonight, has been my rock, as I said before. Up here, pictured standing by the Grizzly Creek as it flows out on the way up to the mountain. This is Pino, the llama. He's a good friend of ours, and he helped carry all our gear to the base of the mountain. He was super instrumental in getting us up there. Forrest, again, pictured here, and here's this zoomed in image of Copper looking very small under a heavy backpack on our way up to the glacier. Oh. And of course, Dana York here, pictured debating whether or not a sedge was the sedge I thought it was on his way up to the mountain. Dana wouldn't like me to say this, but here he is putting a poncho on as we get dusted with snow. I think he was worried he was going to melt, but he didn't. He's fine. It's okay. And so what this really led to was a home away from home. This was our camp as we had it set up on the mountain, auspiciously above this giant cloud of smoke. Don't get me wrong, it was really beautiful, but it was interesting place to call home for the 16 days we were up high. But as you can see, beautiful scenery and a really amazing spot to call home for a little bit. So onto the methods we used. I've been talking about changes through time, and what I immediately think of personally when I think of changes through time is visiting one plot year after year after year. That's probably how we're most familiar with it. But there's this idea of a chronosequence, which is that time is related to distance from the most recent glacier extent. And so what we can think of here is that the further you are from that most recent glacier extent, the older the ground is, i.e. the older it, or the longer period of time it's been exposed. If the glacier was, say, this long, 100 years ago, and over that time retreated back further and further away, this spot has been exposed for much longer periods of time than the subsequent spots that are closer and closer. So that's the kind of assumption of the chronosequence. It's frequently used in ecology and is often used in these glacial ecology studies as well. We also wanted to look at vascular and non-vascular plants, which came with its own host of issues. I'm barely a botanist, let alone a bryologist or lichenologist, I think is the right word. So we had to call on some expert help from Jim Shivak at the Cal Academy of Sciences to help us ID the bryophytes. And basically, we use plots of 5 by 5 meters, so 5 meters squared, collecting data within these plots. And we place these strategically farther and farther away from the 2014 extent of the glacier. We collected data on the plants, their cover classes, i.e. how much cover they took up of the surface, the soil texture, and we did this over 15 days in August of this last summer. So this is an example photo of one of the plots that we would set up. You can see here we have the tape placed across the glacier. As you can see off the bat, there's not a lot of plants. And so scrutinizing cover is notoriously difficult. It took a really long time to set each of these plots up and took a lot of debate as to keying out the plants. So it was an arduous process for each plot, that's for sure. This is our study site map. It seems a little confusing at first, but it's really easy to break down. Each one of these pink dots represents a plot where we drop our 5 by 5 meters on. We would study the plants that were in that area. They're each a corresponding distance away from the midpoint of this 2014 glacier extent, and they extend and cut across these other colored lines. Each one of those colored lines represents a different time that that glacier was present. Data extents came from Garwood and his publication at 2020, which is super useful for us. And basically you have in the purple, 2014, 2013 in the blue. The light green that's quite hard to see on this screen is 1994, then down into the yellow at 1972, and again into 1955 in the orange, and then 1850 for the red, which is the date that the glacier reached its maximum size. So each one of these has a corresponding distance that you can calculate and therefore some kind of corresponding age, i.e. the further you are away from the green dot in the middle of the purple polygon, the older the ground is. So the questions that we ask is, how do plants change over time? With the resolution of data and for the benefit of this presentation, I've broken these down into graminoids, forbs, shrubs, trees, bryophytes, and lichens. Graminoids being the grasses and sedges, forbs being our more typical herbaceous flowering plants, shrubs, the sort of woody intermediate between those and trees. Trees, that's a given. Bryophytes being mosses, and then lichens. What we see if we look at one of our transects that cuts across this time period is that there's differing rates. On the y-axis here, we have the percent cover, and on the x-axis going from left, we have our oldest plots to right, our youngest plots. And we see something that we'd expect here, which is that as plots get younger and younger, the covers and also the biodiversity of these plants are decreasing. There's more biodiversity in older plots than there is younger. But we get into a bit of nuance when we compare this transect with another transect. I want you to focus on A, the percent cover here is much lower. So transect B just had lower covers out of the gate than transect A, even at the oldest plots. And it also has these weird peaks that are really different from our other plot. I wanted to know exactly what this meant, and what we thankfully collected data on was the type of habitat, how wet or dry they were. So here, even though it's a little backwards, we have the blue representing drier sites and the red representing the wetter sites. And again, on the far left, we have our oldest plots, and on the far right, our youngest. And if you look at that blue line, it's steeply declining. So as age increases, we see a massive increase in the species richness and the total cover of our plants. But that's not the same when we look at our wet sites. So plants are more rapidly colonizing along these riparian ecosystems, along mesic corridors. And that's sort of an interesting notion as to one of our environmental variables that might be significant in terms of our analysis later on. So again, really just wanted to focus on the shallower gradient of that red line compared to the steeper gradient of the blue line. So that's a bunch of graphs, and what we really want to discern is what that means for more digestible kind of information. Picture here in the top left is Carex spectabilis, the showy sedge. This forms the dominant plant cover in the oldest sites. As you can imagine, this didn't just grow over the course of 10 years. That's taken a long time to grow into such a large mat of this plant. So that was our dominant late successional stage plant. Interestingly, along with that, down here in the bottom right, we have the Ethereum distentifolium, the alpine lady fern. This is also typical of our older successional stages. It takes a very long time to develop and grow. It needs good soil. So that was another one that was seen frequently in our lower successional sites. Up higher here in the top right, we have Luetka pectinata, which is the partridge foot plant. That was more tolerant of our gravelly sites. It was an earlier colonizer. It didn't need as much water. And so we saw it more prevalently the closer we got to that 2014 extent. And then the two pretty flowers are both members of the monkey flower family. They're both erythranthe. Bottom left being Erythranthe tinglii, and the middle pink flower being Erythranthe lewisii. These both colonized really rapidly along the riparian systems, along the mesic corridors on this glacier. And so they were kind of this early colonizer if water was present, but they need the water. So another really cool finding that we had, which is kind of adding to this confirmation of literature, is Carex vernacula. Before Justin Garwood went up there with some other researchers, this had been undescribed in the Trinity Alps. They made a collection of it and brought it back down, presented it. Gordon Lepick, who I'm sure many of you know, keyed it and said, yep, this is Carex vernacula. What's interesting about Carex vernacula is that it is not listed in the Jepson as a species present in the Trinity Alps. So by us finding it, we're furthering this idea that there is a range extension potentially needed for this plant. It's a relic. It's not found anywhere else. We didn't see it one time in our entire summer of mapping vegetation. This is the first time we saw it. And funnily enough, it's referenced by Furlot in his Flora of the Trinity Alps, growing specifically beneath the ice fields, as he terms them, on the north side of Thompson Peak. So this is kind of a really interesting reaffirmation that maybe the Jepson doesn't know everything yet, but it knows a lot more than me. So question 2 is kind of more nuanced. Are there indications of competition increasing through time? So we can think of competition as someone winning the race. This is notoriously difficult to parse out in terms of field ecology, and it becomes a very difficult thing to study in the field, especially in remote places when you don't have time as a luxury. So what we did is make use of this mathematical diversity equation, which uses pairwise comparisons. It's a fancy way of saying it compares one plot to another and sees what was present in one plot and what is absent in the, and is it still present in a later plot or is it absent? So it states that diversity between sites, the difference in plants between sites, is related to a factor of replacement and addition. Either species are being added to, and that's creating differences between the two plots, or they're being replaced. So you can think of addition as if I have 3 plants at time 1, and at time 2 I have 5, but the original 3 are still there, they're being added to. But if I have 3 plants at time 1 and 4 plants at time 2, and only one of these plants at time 1 is still present at time 2, they're being replaced ecologically. Their functional role is kind of being overruled. It would not include hybridization because we're only keying things to species, but I wish I had a genetics lab. That would be great. So again, species that are replaced in the timeline, we can think of replacement as indicating the prevalence of early competition in a successional environment. If a plant was present in time 1 and is no longer present in time 2, we can think of it as being outcompeted. And then species that are being added to is a lack of competition in early successional time and a prevalence of linear succession. And these equations also factor in percent covers. So it's not just saying presence or absence, it's talking about relative abundance. So let's take an example from one of my transects, looking at the Sorensen index of beta diversity, which is a fancy way of getting a number that means just about nothing to us right now, a total of 0.477. I don't even know what that means. But if we look at that in terms of the proportions of replacement and addition, we can see that in transect A, about 21% or 0.21 was accounted for by replacement and 0.78 was accounted for by addition. So what that actually indicates when we break it down by plot is we can come up with this fancy chart that shows the relative amounts of replacement or addition over the course of our plots. Again, left axis oldest, right axis youngest. So if you focus here on SGA 6, this plot here, right around the middle of the age ranges, it's not too old, it's not too young. Almost all of that is attributed by addition, which shows that most of the plants here were only added to in later stages. Whereas if we look at this early successional stage here, SGA 11, a very young plot, there's a relatively higher amount of replacement going on here compared to the others. And so maybe that indicates that, yeah, a lot of the species present in our earliest successional environment are being replaced, either in terms of their abundance or their presence or absence. Again, early days, this hasn't undergone like full statistical scrutiny yet, but these are the trends we're seeing. So again, higher contribution to species addition, more shared species, and here, a higher contribution to species replacement, there are fewer shared species. So where do we go from here? We're going to use the data we collected this year that you guys helped fund and get off the ground, and we're going to use that to inform our strategies going into year 2 of data collection. We're going to return to this foreland, this glacial scar in August and September of 2025. We're going to collect the data we have left on the remaining plots that we have to get. And then we're also going to start to look at this facilitative relationship between vascular and non-vascular plants and hope to answer that question as well. And at some point in time in this entire process, I will write a thesis, I'm sure of it. So in summary of the trends that we see so far, the cover classes and biodiversity increase as we go from younger to older sites. And that's something we expected to see. It's a no-brainer that as time goes on, in an early successional environment like this, species richness is going to increase, as will plant development overall. Variations within these trends on the transects can be contextualized by habitat data. If we remember, there were different peaks of covers depending on which transect you were on, and we can sort of scrutinize that in greater detail by looking at whether the plant was found in a wet site or a dry site and what kind of plant it was. And we already have the potential for replacement-based succession observed within certain species. So if we just looked at biodiversity overall as a factor of species richness, we'd see biodiversity increasing through time. But that's not scrutinizing whether we're losing or gaining certain species over that time. It doesn't care for the one grass that was present in very small amounts that's being outcompeted. And so hopefully throughout the course of this project, we'll be able to scrutinize that in more detail and ultimately answer the question as to whether or not there are species that we're losing in this ecosystem. There are several limitations to the study as I have it so far. It has a relatively small sample size, and that's the reason I can't give you guys this magical 0.05 p-value of significance yet. And also the chronosequence itself, this idea of distance for time, it assumes some linearity. And we've limited that as best as we can. We can contextualize it with the glacial retreat data that Garwood mapped out in his 2020 publication. And we can use multiple transects to try and spread them across the glacier to try and account for the various rates of retreats that we have. And the last limitation that we really have is the weather. While we were up there on night number 3, we got hammered by hail, lightning, 40-mile-per-hour winds. And then right at the end of our trip, we got about half a foot of snow dumped on us, which cut things a little short this year. Nonetheless, everyone made it off the mountain okay, and it was all fine. But it's definitely a limitation when you're trying to identify a plant and it's been pummeled by hail. So with that, I'd like to open it up to any questions and also highlight that at the back of the room, there are a bunch of pressed specimens of some of these really unique and beautiful plants that we collected, arduously brought down off the mountain and pressed, and have curated for you guys here. But yeah, that's the presentation as it stands.
So I think we'll try to get the whatever they're called, those people. We'll make it so they can chat. Oh, there's already 8 comments.
Oh, God.
Oh, it's probably not.
8 comments doesn't sound good.
Very dark in the hall.
What is
What is this business about moth? Oh, that's just, okay, they're not for you, I'm sure.
Oh, thank God.
But anyway, they can ask them here now, and we'll try to answer, we'll try to get them communicated to you. So, and also please repeat the questions.
Yeah.
Put those in.
Absolutely. Go ahead.
So, can you picture scenarios where replacement will happen with no competition involved?
Yeah, there's definitely the potential for replacement to happen as a result of environmental variables changing. As far as measuring competition in the field, there aren't a lot of really proven methodologies to doing that without a ton of time in the lab, controlling and looking at spacing between plants. It's pretty arduous to do in the field. So as far as like really hammering down like competition, you would probably have to repeat the same procedure, but looking at specific interactions between plants. Those scenarios where something might be replaced is if something is a really decent plant at taking advantage of low soil development, and over time, just naturally soils develop more. And so other plants may take advantage of that better than an early pioneer. That's a definite possibility, and we can't rule that out. So again, these are just indications.
So, just to extend my question, that how would you distinguish competition from simply one species or type winning? What makes that win or that replacement as a result of competition?
Oh, yeah, definitely. I think that's something that's been debated yeah. So the question was about what differentiates replacement from competition, to some degree. But
What is this? What's the meaning of competition? It's more than simply winning, right?
yeah, definitely.
What is?
Yeah, so when we think about the replacement measure here, if we were simply looking at it as a presence or absence matrix, it would definitely be that you can't kind of look at that. So either a plant's there or it's not. But these diversity equations and this mathematical decomposition, it takes into account the relative abundance of the plant. So even if a plant is still present later on, it'll still pick up some signal towards replacement if its relative cover in the plot has been reduced. So for each of these plant species, we're not just recording whether it's there or not, we're recording its actual abundance relative to everything else in the plot. And when that relative abundance is factored in, it kind of helps tease out, okay, is this actually competition? Or like in actual fact, this plant isn't just still there, but it's there in a lower amount than it was before.
There because it can utilize resources better.
That would be something that yeah, that would be something that you'd need to tease out in a later study for sure. If you actually wanted to say like, okay, what are the brass tacks biological reasons behind this replacement? That's the thing that this is an indicator of competition, not necessarily competition itself. Replacement based theory and this stochastic change of plant communities over time, it's not necessarily directly related to competition. It's simply informing us whether there is competition or not. And the end result to the plant community is relatively the same. Whether or not it's competition, there's an overall species loss through time. So you kind of have to figure out the nuance later on in more detail. Go ahead with that question.
Is the purpose of revisiting the sites this next year, is that to like compare year to year, or is it to like bulk up your like?
It's to bulk up the available data, yeah. I would, if to compare year to year, we'd need a much longer window of time. These plant communities in this alpine environment with the low growing season, you would have to revisit these plots after 50 years. And I really like going to grad school, but why should be done before then? So this is a good substitute with the distance for time. No, there'll be different plots. So we collected data on around 60 of 120 plots, somewhere in that neighborhood off the top of my head. And so we need to go back and finish the other ones. So the other thing is the signals from this data are largely relegated to a lot of the plots that are lower down in the glacier. And we're likely missing a lot of the remaining information from younger plots that are further up in the age structure. Okay, that and then that.
So did you go through here and see this area and want to study it, or did you hear about it?
Yeah, that's a great question. I read the paper that Justin put out in 2020, right after I graduated undergrad, when I was in Tennessee. I read the paper he published and I kind of had it like bookmarked. I was like, maybe I'll go to grad school. And when I applied to grad school here, Lucy had a couple of projects open and I was like, no, I really, really want to do like this thing. And I was really stubborn about it, which in retrospect, I probably could have done a lot of things that were maybe a little simpler, but yeah, it was definitely a long time coming for me to want to do this. And then one question back there. Yeah.
Your plot layout that you described there, how did you, and maybe it was Darwin's paper, that how do you determine the youngest, like which one had been the oldest versus the youngest? I'm just curious because your design was based upon that, and I didn't quite.
Yeah, so actually there's two gentlemen back there that probably speak to it a little better than I can, but they basically looked at historic imagery and they geo-referenced through these historic photos where the glacier was at certain time periods. They took that 1955 photo and geo-referenced it and mapped where the glacier was. They found another photo in 1972 and geo-referenced that and basically mapped these dates out onto the foreland using remote sensing techniques and eventually created this kind of chronosequence of how that glacier retreated through time. The projected points I used are just along a transect that bisect those at different angles as they go out from the midpoint of the 2014 glacier. Yeah, remote imagery. Yeah. I have a question up here that I have to answer. I don't know the order. Yeah. Does the intermediate disturbance hypothesis not apply because of the glacier? Great question, Tyler Fisher. Does the intermediate disturbance hypothesis not apply because the glacier is retreating with climate change and not fluctuating back and forth? We can't rule out whether the glacier fluctuated back and forth. And as a result of that, the benefit of the transects that we have is that it doesn't matter if the glacier prograded and retrograded, it's still that time since deglaciation is going to be related from distance. There's obviously some nuance to that, and we hope that by spreading our transects out across the glacial foreland in multiple different angles, that we'll be able to capture some of that variability and maybe mitigate some of it to some degree. But yeah, there's no way of ruling out whether between 1955 and 1972, the glacier grew a little more and retreated further. At the end of the day, the rule applies that the farther away you are from the midpoint overall, not specific to a date range, the older the ground is. So hopefully that answers that, Tyler. Yep.
I don't have a real scientific question. I'm just
Thank God.
I just missed where you are. I'm trying to picture because I've been to the lake a number of times, but not for a long time.
Oh, definitely. Yeah.
So where
I can walk you into it. So if you're at the glacier at the waterfall and you're looking up at Thompson and looking across Grizzly Lake, there is a large ridge to your left as you're looking south. At the top of that ridge is a saddle, a low area in the terrain. If you cross that saddle into the next drainage, there you'll find a moraine that's, I mean, clear as day. You can go up there and you're like, this is not normal. There's something weird going on here. So it's just up and through that ridge. So it's basically the farthest you could go from anything. To the left. Yeah, up through that ridge. Yeah. Okay.
To further help explain some of the variation you're seeing between your plots and your transects and whatnot, are you collecting any site attribute data like soil, moisture, soil composition?
Definitely, yeah. So I would have loved to have gone into more detail. There are a lot of postdoc research papers out there that really get into the nitty-gritty in terms of soil pH and even further into the weeds by looking at the kind of microfauna that's there and everything else. For this, we used an adapted rendition of the CNPS published Releve protocol. So we collected data in terms of soil texture. So for me, the most meaningful covariate there would be the summation of the amount of the ground that's covered by gravel and fines as sort of bioavailable substrate that plants could colonize onto. Slick rock doesn't really harbor a lot of the plants. And then we also took data on aspect, the percent slope, sort of these other covariates. But yeah, definitely would be interesting to see more detail on that in the future, but just don't have time for all of it. Yep.
Well, I think the mosses actually are kind of an indication of how wet it is. So even if you're not interested in those particular mosses, the amount of moss would probably be an indication of how much water you got. And then kind of related to that, like you talked about competition among the vascular plants and then facilitation between mosses and vascular plants. But to go back to what Larry was saying, I think what you really have is like these signals of things rather than the things themselves. And so I don't think I would, maybe I would guess that the vascular plants might be more of a signal of competition, and the bryophytes have more of a signal of facilitation. But I actually think that what you would do is just look for the signal of facilitation, regardless of where it's coming from.
Definitely, yeah. The key thing we're interested in here is you could run looking for the signal of facilitation even between vascular plants. The methodology I've picked, I actually have a slide for it just in case this came up. Oh yeah. Oh man. Okay, so the way that the facilitation, again, a notoriously difficult thing to study in the field. Part of the reason I left out this convoluted slide with a bunch of equations, but basically it's, again, just the signal of facilitation. It uses relative covers near vascular plants versus outgroups. And so for sure, there's definitely still the potential at competition and facilitation to exist within different groups of species. Like you could have facilitation between vascular plants, but the way this relative interaction index works, which is just a spatial interaction and just an indicator of facilitation, is it takes the relative cover of a moss near a dominant vascular plant versus where it's not found near that dominant plant, and you see if they're correlated spatially. So again, this is field methods to try and describe something that's typically done in a more controlled environment or with much longer periods of time available to study it. In terms of the competition, though, what's cool is that the beta diversity equations, they are across species. So you'll see replacement in bryophytes as well. It's just a presence absence matrix of everything. So again, it's not specifically competition, but it's this indicator that maybe there's competition. Say you have a ton of bryophyte cover early on, and then later on in the successional series, you don't have as much bryophyte cover, it'll pick up that signal. Does that mean that there's competition between vascular plants and bryophytes? No, not necessarily, but does it inform research efforts to go back and really scrutinize individual species? Yeah, it might do. So it's kind of doing what we can with what we've got in the basically month-long growing season on Thompson Peak. So I don't think there are any other questions in Zoom. Oh God. Uh,
And read the question, just like, what do you know about white bark pine up there?
What do I know about white? Well, about 2 months before we did this, me and Forrest were up there doing vegetation plots on white bark pine. We actually went to the spot where they burned relatively recently. Seems pretty obvious they're in decline. There were no seedlings present in any of the plots we did in the white bark pine up there, so they burnt and they're not regrowing. Seems like they're in decline, but there is still a healthy amount of white bark pine. They seem really relegated to just the ridges though. They were like nowhere other than the ridge tops. So there might be a forest of hemlock all the way up, and then right at the top on the apice of the ridge is a ton of white bark pine. It's not found anywhere else. The same up behind Grizzly Glacier. So not a species of interest for this study, or it is a species of interest, but definitely not the focus of the study. I can only talk to it from other work we've done.
But it is colonizing adjacent to
The glacier.
scar in the terminal moraine that we're seeing.
Yeah. So around the edges on that big mound of debris, there was white bark pine seedlings there. It's hard to say whether they it could have been there for a long time. Since 1850. Yeah, there wasn't any white bark pine in the actual glacier itself. So it's not colonizing there, at least. We can say that. But it might do. Give it another 100 years.
All right,
Cool.
well, thank you.
Yeah. Thanks, everybody.
If people have further questions, maybe you'll mingle a little bit, and I think you can both go